So today, thank you. So today we are continuing the theme on SEASTAR, the sort of build up to the user consultation meeting in Bucharest in October. And we have a presentation by Antonio Bonaduce and Øyvind Breivik, who are both members of the mission advisory group for SEASTAR and are going to be talking to us about one of the case studies that we have submitted to demonstrate the value of SEASTAR in the case of the Norwegian case study. So over to you, Antonio. I don't know how you want to manage this between you and Øyvind, but I'll let you take over from now. Okay.
Teams, Øyvind and I already agreed how to do it. I'll start. So first part will be me, and then I will leave in the floor and I will continue. So let's say the title was already explained by Christine, so I will try to go directly to the outline. So I start just to frame a bit the aim, the general aim of this seminar. So let's say the science goals of SEASTAR and how relevant this can be for the candidate mission. And as Christine said already, we managed to make a case study for SEASTAR in the Norwegian seas. And in particular here, I want to talk about, and this will be the first part of the seminar, about what we like to call a natural laboratory that is in the Lofoten Basin. And I will spend a few words to characterize it. And then we will follow up with the characterization of the Norwegian coastal current and fjord system that are characterizing the current itself. So and then will be Øyvind continuing on this topic, and then some take-home messages. So first, I just go quickly here because this was already introduced, I think, a couple of weeks ago, or at least shown by Christine about the Earth Explorer, but just, let's say, just to make again the point, so SEASTAR is a candidate mission in the 11th phase of the Earth Explorer program that started quite a while ago. I think our first mission was launched in 2009. So last mission was let's say, the last candidate mission was Germany, that now was accepted last year. So and then SEASTAR at this phase is a candidate mission with other four. I will not describe the others, but I will just say that this is the only ocean mission that is in the Earth 11 Explorer, Earth Explorer 11 phase. So, and then which are the, let's say, the general aim here. I think this picture is very nice. So, and makes a very good point. So we want to reveal which are the fast dynamics at the ocean margins. So, and then when you look at the science goals, so I think the very first one, it explains why this is relevant. So resolving fast evolving small-scale ocean dynamics and mediating exchanges between land, cryosphere, marine biosphere, and atmosphere is something that is still not known into the detail at all. So what is definitely making a difference in SEASTAR is that it aims to resolve coastal shelf and marginalized zones. That means what we are talking about margins, let's say, and then to a general extent to contribute to reduce the uncertainty when it comes to the contribution of coastal shelf and marginalized zones to in the global system. So then here I'm showing what is the SEASTAR sampling. So what is called the COSMIS. So all the coastal and shelf areas in the global ocean. This is a missing point in the observing system, definitely, and the marginalized zone, and a number of sites of special interest. I start from there to introduce the area where we want to focus today. So this is an area that can, of course, will be sampled by the SEASTAR vision. So this is relevant for the Norwegian coastal current, but I will also talk more about what you can see, that area that is highlighted in that blue circle, that is the Lofoten Basin. So In the next slide here, I like to characterize a bit the general circulation in the Norwegian seas. So as on the left, if you look at the red arrows, then you have the pathways of the North Atlantic waters going to the Arctic. So, and then you have the separation in the two branches, that is the slope and the frontal current of the Norwegian current. And in the middle, there is the Lofoten Basin. So the exchange and maintenance of the system among the two branches is not yet well described. Is known that it's mediated by EDIS, but is not yet described into the details. The figure here shows also the pathway of the Norwegian coastal current in green that we will characterize later on, and also Øyvind will continue on that. And also here, if you look at the left part where you have blue arrows, it shows the patterns of, so the pathway of the Arctic waters recirculating along the Greenland coast and in the Greenland basin. So I'll continue talking about the Lofoten Basin, and it's a basin that what is typically defined as an eddy-rich areas or an hotspot of mesoscale dynamics at the high latitude. And here in the upper right panel, I show the distribution of eddies that can be detected nowadays from satellite altimetry, for example. And then when you have the opportunity to make a collocation with Argo profiling floats, then you can study what is the vertical profile, so the kind of 3D structure of this kind of eddies. So all these things are possible today, relying on the collocation of Earth observation and autonomous profilers. But what we are relying on is geostrophic currents, and we can resolve scales that are not as fine as, let's say, we cannot go down to some mesoscale. We can constrain the mesoscale to a certain extent, but if we want to go beyond, the observing network available nowadays is not sufficient. On the other hand, when we look at the synergy in this kind of areas that are rich in eddies with other sensors, so here I'm showing an example of a collocation between Sentinel-3 chlorophyll concentration during June 2020, meaning that at this latitude having a cloud-free condition is essential to observe this kind of features. And then it's well known that there are features that are way smaller, and then they have an impact on the biology in the ocean. And even more, if you have the opportunity to compare with surface roughness, you can see even more, which is the complexity of the horizontal gradients within these features. Here in particular, you have what is called an hammerhead eddy, so where you have an anticyclone and a cyclone occurring together, and they are inducing, let's say, positive and negative anomalies in the chlorophyll concentration field. So then we know that this kind of variability is essential to understand the connection between ocean dynamics, biology, and ecosystem, but still we cannot resolve it nowadays because these kind of observations are not systematic. We can still have always nice acquisitions, but we cannot make a systematic assessment. So here, same patterns, same, probably not exactly the same feature in the same day, but was collected also by MODIS. So if you nowadays play on this very outstanding opportunity of multi-sensor synergy, you can characterize this on, but not on a systematic base, I would say. Then what is also important to consider is that nowadays, what we typically know about eddies is that when you have an anticyclone, so that I call ACE, so the top left panel, typically you have a downwelling. And while when you have a cyclone, you are typically associated with an upwelling. And this is what is described in the top panels here. So you have chlorophyll anomalies, and then the contours instead, let's say, is the sea level anomaly. So then if you have an elevation or a depression of the sea surface. Instead, the bottom panels are more interesting, or let's say, because here the air-sea interaction kick in. So here when you have, for example, an anticyclone, it's worth noticing in the basin that there are also positive anomalies of chlorophyll. So meaning that you have an upwelling also when you have in the occurrence of an anticyclone. And the opposite applies also to cyclones, meaning that you have downwelling when you can have cyclones. Here, the contours are not the sea level anomaly, but it's the Ekman pumping computed from scatterometers. And here, the message is that here's the interaction between the eddy-induced currents and the stress of the wind that is generating a positive or negative Ekman pumping that is prevailing on the eddy pumping. And then you have this kind of characterization of the mesoscale that relies on ACE interactions. And then if you can have currents and wind simultaneously, acquisition of currents and wind simultaneously, you could reveal this pattern in the ocean that is not obvious that you can always do. What we also had the opportunity to explore in the basin recently builds on SWOT. So SWOT in particular, the fast sampling phase of the mission. So 1 day repeat cycle. So one of the crossovers was located in the basin. So we started what is called an early, let's say, as an early adopter initiative. We adopted the crossing over and started to look at it. So in the first panel where you see the animation, you see the added value of having 1 day observations when you can have eddy-mediated processes that are connecting the shelf. So say cross-shelf exchanges, this can be distinguished very well. And of course, the evolution also of a very stable feature that is the Lofoten vortex, typically an anticyclone. And here you see the pattern in the elevation. This was panel A, while panel B, it shows the dramatic improvement in terms of sampling, spatial sampling, compared with what is available nowadays in terms of level 4 altimetry, from level 4 products for altimetry maps. And then we started also to try co-locations with other missions. And in particular here, if you look at panel C, I'm showing how SWOT and radial velocities derived from Sentinel-1 Doppler shift can have a nice synergy. Here we have features that are from Sentinel-1 Doppler shift. They are revealing mesoscale features, and some of them are very well collocated with SWOT. And again, if we look also at Sentinel-1, so then we see that it's not only the large feature, but also nice features, the small features that can be resolved by this mission and collocated with chlorophyll patterns, for example. So here I tried to make a point on the importance of having 1 day sampling. That is also what is SEASTAR aiming for, at least during the phase of the mission. But then what is also important is that to keep in mind that you have accurate observation of surface currents at 1 kilometer resolution. The accuracy is important. And here we are making a kind of investigation on how the error is growing to what is called the representation error as a function of the resolution in a model. Here we use a model that is called the NERSC model, is resolving very well at 800 meters resolution the Norwegian coastal current, and not only. And then here we consider different horizontal breeze spacing, and we see how the error is growing. So then we are in the order, let's say, of 0.1 meter per second. That is the one in the order of the requirement for SEASTAR. But then if we compare it with the variability of the field, and this is the ratio of the error and the variability of the field itself, we see how relevant is having such an accuracy when you go down to kilometric resolution. So if you don't have that, the error is getting larger than the variability of the field itself. So I think this can give at least an overview of how on this requirement for SEASTAR. So, and then let's say to summarize how we see this, so the study on the Lofoten Basin and the Norwegian coastal current relevant to SEASTAR for sub-mesoscale dynamics, cross-shelf exchanges. So when it comes to fast dynamics at ocean margins, this kind of processes are more than relevant. And then also for the sampling. So some having the added value, having what they repeat orbit, like SWAT Calval phase, and also the requirement in terms of accuracy when you go down to kilometric scales of sampling. And Øyvind, I think, will continue. So Øyvind, the floor is yours. Tell me when you want me to show the slides.
Thank you, Antonio. So Antonio has given you an excellent introduction to the open ocean conditions that are still within, let's say, the planned coverage area of the SEASTAR mission. I want to take you closer to the seashore. I want to take you into a very complex area where you have an interplay between the Norwegian coastal current, which is flowing swiftly northwards, if you skip to the next slide. And it interacts with, in some places, extremely strong tidal currents. I've chosen the Moskenes current for this example. On the right, you can see an example with a Lagrangian model, which just gives you a feel for the kind of strength that you're looking at as the tide is going in and out through the sound. What makes this unique is that it's one of the strongest open ocean tidal currents. So on the west side of the current, you have the full Norwegian Sea, which means that current wave interaction is rife in the area. It is an area which is really is well known for the complexity of the sea state, and it appears that the tidal current can reach probably around 5, maybe up to 6 meters per second at the peak of the tidal cycle. In fact, we don't know precisely because it's very hard to do measurements. We've done measurements off to the side, and we measure 3 meters per second, which is already very strong. What I think is interesting about this case is that it describes many of the scales that are relevant to the SEASTAR mission. It shows that you need measurements of waves, you need measurements of currents, you need measurements of winds, and you need them at scales down to a kilometer in order to be able to capture these features. So if you skip to the next slide, Antonio. This is an example of 2 MSI optical images taken at outgoing tide on the left and ingoing tide on the right. If we focus on the left map, we see that there is a clear velocity front as the tidal current is going out. That meets, in some cases, swell, in other cases, and more usually wind sea. And you can imagine that this makes for rather complex sea states with the strong current gradients that you find in the area. In addition to that, I think if you skip to the next slide, you have the Norwegian coastal current, which is flowing north in the area, and where there is a 7 and a B, the ADCP, is roughly where this tidal current is located. So you can see that the coastal current, which is driven by the baroclinic differences from the freshwater runoff and the extension of the Gulf Stream as it flows into the Norwegian basin, more or less hugs the Norwegian coastline going north. And it adds to the complexity of the whole region here. And the Norwegian coastal current itself is quite strong. It's got a speed of typically up to 1 meter per second, and it's got strong eddying motion. So we have a case where we have strong tidal currents in certain locations. We have strong eddying motion up to 1 meter per second in a lot of places. And if we skip to the next slide, this makes for some rather complicated navigation. And what you're seeing here is a map which is taken from the Norwegian Pilot Guide, which highlights a number of so-called dangerous areas for seafarers, and it's related to complex sea states and wave current interaction. So what we wanted to know, and without any in itself connection with the SEASTAR mission, but I'll show you the connection soon, is can we identify areas that we see as having a strong wave current interaction? And if we skip to the next slide, I'll give you an impression of how we did that. This is a snapshot of two different wave model runs at 800-meter resolution. One is with current refraction and the other is without, and what you're seeing is the difference. So you're seeing that at any given point in time, there will be differences due to wave current interaction on the order of 0.5 meter. Obviously that depends on the sea state, but that's typically what you see. So 0.5 meter is quite significant if you have a plus minus 0.5 meter on that. So we can identify directly that there are a lot of areas that see very serious wave current interaction in this region. If we skip to the next slide, you will see that what we've done here is that we've done a Fourier transform with a double bandpass, and we've colored it pink for the regions where eddying activity dominates. So the part of the spectrum, this is not the wave spectrum, but the spectrum of current activity, which is typical for eddy activity. And green is where you find that tides dominate. So what you're seeing here is a map showing areas where there are large differences due to wave current interaction between these two wave model twin runs, the one with and the one without current interaction. And we've identified it as either eddy induced in green, no, in pink, or tidally dominated in green. And where the white arrow is where you have the strong Moskenes tidal current. And obviously, and unsurprisingly, that shows up as bright green, because we know that it's a tidal current. But what is also interesting to see is that there are plenty of areas where there is no clear tidal dominance, where it's clearly eddy dominated. So it has to do with the interaction with the coastal current and on the outside where you have open ocean with swells and wind seas coming crashing towards the shoreline. And in fact, we can not only reconstruct the pilot's guide, we can identify the areas that have been empirically found to give rise to dangerous sea states, but we can also identify quite a few new ones that were not really identified. And among those is a number of those listed on this map. I won't go into the details of that, but I think that this scale shows you something about the value of having an instrument like SEASTAR, where you can measure at the same time the currents, the winds, and you can get an estimate of the wave spectrum on a resolution of 1 kilometer. And that's important, because if you have coarser resolution, as Antonio also said, if you have a coarser resolution than that, you're starting to miss the scale at which these processes are present. I think we can quickly go to the next slide. And I'm coming quite close to the end now. You could ask, does it matter? I mean, Norway has a long coastline and not so many people. It's on the order of 5 million people in this country. If you look at the traffic data, you can see quite clearly that there is a number of, this is AIS data from the Norwegian Coastal Administration. And it shows very clearly that the typical lines of local coastal maritime traffic are smack in the middle of that area where you have all these wave current interactions going on. The two thick, bright lines that you see at the outermost edge are traffic lines for oil tankers, partly coming from Murmansk. So that is to remind you that this is a region which is also trafficked by huge tankers carrying enormous amounts of oil, which again means that precisely the scales and the coverage which is planned for SEASTAR, I think will also have a potentially large societal value in identifying these dangerous areas. If we skip to the last, I think the last slide. I would like to just summarize the relevance to SEASTAR as I see it, and as Antonio, I think, sees it. It is that waves and currents tend to conspire to make the coastal zone one of the most difficult regions to model. And the scales that are typically found in the coastal zone are very well matched to the resolution that SEASTAR aims to measure. And the variables that are needed to study wave-current interaction are precisely the ones that SEASTAR can help provide, namely kilometer resolution, currents, winds, and wave spectra. And what you're seeing, the animation which is flicking past on the right-hand side here is again a number of snaps of the differences. So you can regard the colors as the impact of currents on waves. So you can again see that in this strong tidal current, as the tide goes in and out, the wave field will be modulated on the order of plus minus half a meter. And that's really quite a lot. So with that, thank you.
Yeah, thank you, Øyvind. That was
Thank you very much.
Maybe
Thank you very much, Øyvind.
we also had this take-home message, maybe just keep in mind the last point. So user consultation meeting in just a couple of weeks. So we'll be there. Hope to see many people.
Thank you very much, Antonio and Øyvind. That's a very good marketing for SEASTAR, and the UCM in a couple of weeks' time will be an opportunity to expose these benefits of SEASTAR to many applications in coastal and shelf seas. Are there any questions from anyone? Let me see. Okay, I can't see any. I just wanted to ask Antonio about the Lofoten Bay, Lofoten Basin. So you have this vortex there, which seems to be permanently there. Can you explain what's the principle behind that? Why is that eddy kind of permanently in this area?
Yeah, sure. It's always, again, so it's the interaction of the dynamics and topographic steering. So you have, so the bathymetry there, when you cross the shelf that is relatively narrow, then you get to deeper areas. And then you have the two branches that are basically, if I can make this quickly, maybe just to go here to the initial map. And then you have these two branches, right? And then the Lofoten vertex here, this is the deepest part of the basin, is sitting here, is an anticyclone. It is continuously stealing eddies from the slope current here. And then here is like you get nutrients continuously here, also in this direction. And then resolving this kind of cross-shelf exchanges.
Oh, please, can you mute yourself?
Deve estar alguma faísca.
Rosio, could you please mute yourself? Thank you.
I think I muted them.
Yes, okay, thanks.
Yeah, that's why. So typical explanation, but since, let's say, the relevance is always, okay, of course, nutrients, but let's say there's a reason why Norway, even though has a very long coastline, but it's not fully covered with ice as it would be, for example, in Greenland. So here is how we have all the Atlantic waters coming. So, and then this basin is acting as a kind of sink for HADIS, so, and also for e-transport. So if you can describe how it is the mesoscale and maybe how the variability goes into the sub-mesoscale, you can resolve processes that we still don't understand.
Yeah.
So, and having the opportunity to constrain this variability every day, for example, at least for a period, would be a really added value. Yeah.
Yeah. Thank you. Yeah, and it is very much one of SEASTAR's aims to try to understand the transfers across the shelf break, essentially. So what, you know, how do these coastal waters kind of get mixed or entrained into the more general circulation? Because that will determine, of course, the fate of anything that is suspended in those coastal waters. So thank you. Are there any other questions by anyone?
I have one.
Go ahead, whoever you are. Oh, David, go on. David? We can't hear you, David. Okay. I can't see if you are muted or not, so...
We can move on to Alexander.
Yes. Go ahead, Alexander.
It's not directly related to SEASTAR, but what does drive the Norwegian coastal current, the green one in this slide?
I think Øyvind started already this topic, so I let you go.
Yep. So essentially, the Norwegian coastal current is the accumulation of freshwater runoff all the way from the Baltic Sea and from the Norwegian fjords. So it gathers strength on its way north, and it hugs the Norwegian coastline. But it also meets the Norwegian, the North Atlantic current, which is the extension of the Gulf Stream, which is shown in red here, and that makes for a somewhat somewhat temperamental interaction with the Atlantic water, which is warmer and saltier. The coastal current tends to be fresh or fresher and colder. So there is typically a temperature and salinity front across from the green to the red line as they flow north, and obviously it also follows more or less the shelf break. So the shelf break steers it, and the eddying motion is to a great extent comes from the baroclinicity in the overall field. I hope that more or less answered it.
So, and it's the average strength, like an order of. Can you remind you did say that? So how strong that current is when it gets to like the tip of Norwegian.
On the order of 1 meter per second in many places, sometimes 1.5 meters per second.
So does it become more stable actually as it kind of becomes faster? Or less
rather
stable?
I mean the shelf break, if the shelf break is really narrow, that tends to make it a little more stable, yes. So it speeds up and then it tends to widen and slow down in other places. Yeah. All right.
Thank you very much. Mohammed, do you want to go next?
Yeah, thank you. Excellent presentation. Thank you very much. And yeah, I found the figure with the shipping routes and the information that could be useful for the navigation. I mean, it's just a simple question. Should we expect SEASTAR to help in improving the safety of navigation, at least close to the coast? I know it's not operational mission, it's R&D mission, but is this something that is this add value of SEASTAR for the navigation?
So yes,
can I call upon Christine to go first on that one, because she has a better overview of the policy behind it.
So in principle, the Earth Explorer missions are really sold on the basis of their scientific excellence, but increasingly European Space Agency is looking for missions that are also bringing societal benefits, and also looking for technologies which may be precursors for future operational missions. So there's no harm in demonstrating that there are additional benefits to the data that we will provide. And I think this is a very nice example, in fact, of exactly that, of where, you know, in addition to the measurements, which will be very useful to understand the processes and improve the models, we're actually also providing data that would be of immediate interest to assist with navigation, for example, in this instance. So it's definitely something we should try and highlight at the UCM, because it's very unusual for any missions to be able to tick both boxes. You know, typically we are either very, very good on the scientific excellence, but the benefits to society, wider benefits, are perhaps more remote or not quite as immediate. But in our particular case, we actually are very close at both ends, both at the science and at the societal benefits. So we should definitely make sure we protect that at the UCM. So, did you want to add anything, Øyvind, to that?
No, I think that was excellent. I think the one thing that I might add is that Norway has, since the late 80s, we've run wave models of increasing complexity. But one area which stood out is a region further south where Norway has the kink in the I don't, you can probably not see my cursor since I'm not presenting now, but if you go south to the Stad area, yeah, that's the area. That's an area which is well known for strong crossing seas and strong currents. And so there is a long tradition for highlighting these regions that are known for dangerous sea states due to currents and complex bathymetry as well. So I think that, again, the fact that SEASTAR is gunning for the marginal ice zone and the coastal zone makes it potentially also useful for, let's not call them operational, but maybe somewhat semi-operational studies that could lead to at least unmasking, for instance, regions that are dangerous is one way that I can see.
More applied research in any case, rather than not operational but applied. Yes, definitely. Thank you. David or Mara, who wants to go first? David, how's your mic now?
Can you hear me now?
Yes, we can. Please go ahead.
Well, if Mara doesn't mind, I'll go ahead. I think this is probably mostly for Øyvind, but I heard him mentioning sort of refraction in relationship to the relationship of the currents and the waves. But presumably another factor is getting very steep seas and altering the amount of wave breaking. And that's probably also quite a big factor in terms of the danger related to those seas. Maybe you can comment on that and how much SEASTAR can help in that sense.
Yeah, precisely. I think that's a very interesting question. To what extent we can hope to measure the intensity of wave breaking, I think, is moot. I think that's an open question. Maybe you want to chip in on that, Christine, as well. But in general, you're right. I mean, the wave breaking typically, the wave current interaction will typically lead to shoaling effects, and it will lead to crossing seas where you have at these caustic points where you have an increase in the wave height, and with that increase comes a higher probability of wave breaking. So definitely wave breaking goes up with wave current interaction. That's certainly true. So,
I think
Christine.
the directionality is an important point. The fact we measure the direction of the currents, the winds, and the waves, and at the coast, that is a really important factor. It's not just the magnitudes, but the relative direction of these different forces is really important, and of course very difficult to observe typically, because it's actually still very rare to have measurements of wind currents and waves in the same place at the same time. So again, this is an important aspect. With regard to wave breaking, we're not committing to measuring anything to do with wave breaking, but we are going to have high resolution images from 2 SAR systems, including interferograms at 20-meter resolution. And although we're not committing to anything, I'm pretty sure we are going to see a lot of very interesting signatures in there, particularly from waves, which may at some point give us some insight into wave breaking. But again, it's not a product that we put forward, but I'm sure there will be loads of opportunities from those images. Okay, thank you very much. Finally, Mara, sorry, last but not least.
No, maybe there'll be more questions after. Yeah, I had a question about this work as well, and I was wondering if you could expand on the implications of the tidal versus eddy-driven kind of hotspots in your previous map. In particular, if they differ in their temporal variability and temporal patterns, in addition to the spatial distribution of those.
Sure. Yeah, that's a good question. What we typically see here is that I think these hotspots that are the purple ones, the ones that are eddy dominated, I think they will tend to shift around spatially a bit. This will depend on the sampling period, but it clearly shows that there are strong regions where eddy activity is dominating. And remember, we are defining eddy dominance here in a very simple way. We're just doing a Fourier transform of the difference between the wave height in a wave model run without and one with a wave a current interaction. So we're just simply looking at the difference and we're Fourier transforming that, and then we're asking, in these 2 bands, frequency bands, one which we think is typical of eddies and one which we know is typical of tidal activity, where do we see them? Where do we see these hotspots? The tidal ones will tend to be very stationary. They will always be found in the same places, and that's where the tidal currents are. I mean, tidal currents have been known obviously for centuries, and the one that has been highlighted in my talk is indeed famous from Jules Verne, the 20,000 Leagues Under the Sea, and from Edgar Allan Poe. So it's been in the literature for centuries. So clearly they don't go away. The ones that are eddy dominated, I think, maybe depend a little on the season, but they also tend to have, I think, these locations will be, let's call them quasi-stationary in time. I don't know if that precisely answers your question, but I think in general you will see a similar map taken at a different part of in a different part of the year. This is from a 3-month sampling period from these 2 model runs.
Actually, could you comment on the, we are aiming to do the 1-day revisit, as Antonio mentioned in his introduction. Can you comment about the relevance perhaps of that fast sampling here in this particular instance? Is this something that will be relevant here?
Sure. I think for the eddies, a 1-day sampling would be great. I think that would be really excellent. For the tidal signal, you may experience some heavy aliasing at 1 day. So yeah. I think unless I can convince somebody to shoot up 6 SEASTARs that are marching around the globe, it would be difficult to get around that problem. But certainly for the eddy activity, the 1-day repeat would be great.
Yeah. So yes, for the tides, clearly we're not going to be, providing data to do harmonic analyses or anything like this. The only thing is that if you have sequences of images, of 2D images of currents, of tidal fields or so on, there's a lot of information included in those spatial fields of currents.
Oh, yeah.
And
sure.
if you have sequences of those over a number of days, so here these latitudes we're looking for potentially up to 20 successive days, you will be sampling the tide, obviously not the solar tide because we're in sun-synchronous orbit, but some of the other components will be sampled at a different stage on successive days, which again is something which we hope will be of value to modelers to at least validate their models at those stages of the tide. Okay, great. Thank you. I see, Alejandro, is that another question or?
Yeah, if I may, actually, a couple
okay.
of questions. First, so you guys showed that the SEASTAR accuracy is expected to be around 0.1 meter per second, right? So with that accuracy, do you think we will see the edges in LaFontaine? Is it LaFontaine Basin? So you show like there'll be a soup of edges, but what is the speed around the rim of those edges? Are you going to see them? And then maybe a more general question, like, is there like error model available at this point for this mission, so people can kind of take that error model, add to their model outputs and play with it, like it was like for SWOT in the early stages? So basically, two questions. First, like whether we can see the edges, you think?
That's right. Like, let's say what we try to do here it goes in that direction. Let's say when you mention about SWOT early stages, it depends which is how you define early, because the SWOT simulator was available when the mission was approved, right? And then and later on, I think. So now we are trying to push this concept. It's still a candidate mission. The best we managed to do so far is to take this model that is developed by the Norwegian Meteorological Institute, where Øyvind is actually sitting, and this is resolved in the Norwegian coast. And here we look at the errors, how the error grows if you are coarser than 1 kilometer. So let's say that here we target this 0.1 meter per second that allows to resolve. You see how, so let's say the more you have the more you get to dynamical parts of the Norwegian coastal current, the more the error will grow. That's expected. But if you can resolve at a very fine scale, that you can constrain the variability, and then compared to the variability of the field itself, you have something, this is what I'm showing here, that is let's say is accurate enough to resolve it. Because if you are not there in that range of error, you have an error signal to noise ratio just goes to 1 or more. So let's say this is what we managed to do. When we will be successful, there will be also a SEASTAR emulator or simulator, and then we will play more with this.
Yes, indeed. And Alexander, if you're interested in this, there are so the report for assessment which we have produced for the selection process is available online. So if you go and type in Earth Explorer 11 user consultation meeting, you will get to the page for the event, and there's a document folder or tab on there where you can access the report for assessment. And in there you will see this figure will be in there, but there are also some examples in a little bit later in the report for some model output we used around the California coastal current, where we did exactly that sort of experiment to see, how much of the current field can you retrieve at different resolutions. And what that shows is that the 1 kilometer is really the absolute minimum you need to be able to resolve those currents, those eddy fields. Anything coarser, 2 kilometer or coarser, is not going to give you very much in terms of retrieved current fields. Well, and you will also find in the report, we're also taking it one step further and looking also at the impact on divergence and vorticity, which are two parameters which we hope to produce as well as part of the products that SEASTAR will provide. And again, here the resolution and the accuracy, both of those are really, really critical to be able to retrieve any information about those properties.
Yeah. Well, the actual question, I understand, especially for the West Coast that I know quite well. Yeah, to get sub-mesoscale, you have to go to sub-kilometer resolution, and then you get those sub-mesoscale edges that are have speeds, characteristic speeds on the order of like 20 centimeters per second, right? And then you have measurement with the accuracy of 10 centimeters. That the real question, like, yeah, I understand we should resolve those edges, but they're not like meter per second strong, right? All those kind of divergences, they're like more delicate dynamics, it looks like. So like, there's probably limitation to what SEASTAR can see just because of the 10 centimeter per second accuracy, right?
Sure, 0.1 meter per second is at 1 kilometer resolution. So it is a dual requirement. It's not one or the other, it's both at the same time. So that is a requirement that we're going for. And based on those simulations that we have done using model data, we find that, you know, that is a requirement that gives you some of that information. You're right, if we go finer, it would be better. And we will try to go finer. But we can't commit to a 0.1 meter per second at at finer resolution than that, because that really would push our instrument beyond the cost envelope, if nothing else, of what we can actually do. Because we still have to be compliant with all the requirements from the programmatic context of the Earth explorers. So we will be pushing for finer resolution as well, in the same way as SWOT is now pushing forward both a 2 kilometer product, but also a 250 meter product for the ocean applications. And we will probably be doing something similar, but clearly not with a 0.1 meter per second accuracy then.
Yeah, understand.
Yeah. Okay, very good. Are there any other questions, any final comments or anything? Again, I'll just repeat the user consultation meeting. If you go and find out if you have it somewhere, there you go. You can go onto the website and access the document. If you have any comments on what you read or concerns, please don't hesitate to contact us. We'd rather hear from you before the user consultation meeting than during the consultation meeting, because as Antonio said, we are in competition with 3 atmospheric missions, and these events can be very competitive. It is very much about convincing the kind of general audience of the value of what we provide. So if you do have any questions or so, please ask them beforehand. It will help us to improve our presentations at UCM to make sure that we put forward a good case. So that's my last spiel, my last spiel for SEASTAR today. However, I see there's no more questions, so I will just perhaps wrap up and just highlight that next week, 3rd of October, we remain in the SEASTAR kind of mood, and we'll have another presentation on an aspect we haven't spoken about much today, which is the interactions between the physics and the biology. And we have a presentation by Francesco Dovidio from l'Océan in Paris, who will be talking to us about his work on understanding the role of submesoscales on marine biology, specifically in the case of the BioSWOT experiment, which they ran in the Western Mediterranean during the SWOT one-day repeat phase in the last few months. So very much looking forward to that as another example of where these submesoscale type measurements are going to be very relevant to understand some of those processes between physics and biology. So I hope you can join us. Mara, do you want to say anything before we close? I'll let you close.
No, nothing more. Thank you. Thanks to both our speakers. It was really interesting, and thanks for everybody for your questions.
Thank you very much, and hope to see you next week.